lecture notes. Okay. Okay, we go through this a bit of introduction because this is very important for us to understand. Because we know that in the first session we have actually gone through a different type of materials that can be used. Okay, but basically the the most important character is the material must be conductive or semiconductive, so that can be used on top of our modified electrode. So what is modified electrode? Modified electrode is an electrode made of a conducting or a semiconducting material that is coated with a selected monomolecular or multimolecular ionic or polymeric chemical film. So basically we have electrode, okay, so that on top of electrode we coated with any conducting materials. So the conducting materials that we have gone through last time, like polymers, you know, metals, semi-metals, and so on. So these are the conductive materials that will be coated on top of the electrode. So modified electrode comprise an approach to electrode system design that find use in, okay, the first character that we want to make sure that the modified electrode are very conductive is we want to see the wide angle of spectrum on the potentials. Okay, so we want them to have at least, you know, it can react. Okay, it can have transfer of electron, because we know that the electrode directions is actually heterogeneous. So where we can see the electron transfer between the conducting material to the solution, which is more on ionic material. So hopefully something can change. So this will benefit on the chemical reactivity on the electrode surface. Okay, so we are looking at how electron being transported and change the ionic materials. So the second part is we're going to design electrochemical devices and systems for application, especially if you look at what we have actually gone through much earlier, where it helps in designing most of the electronic devices, okay, like sensors or detector, you know, or maybe like battery, you can actually convert to energy, okay, and you can also look into molecular electronics and other part, all right, that can be used in these particular studies. So the most important feature of a modified electrode is that they are quite thin film, okay, so depends on type of materials that coat on the surface of electrode, okay, and whether it's bonded or just coated on surface of electrode. So this will give some chemical change or chemical reactions, or maybe looking into electrochemical, optical, electric, and others, okay, to behave, you know, different behavior on the surface of electrode. So that's why a modified electrode very much used in industries nowadays, okay, and looking at the potential more conductive material so that it performs the best as a conversion, okay, between energy and also storage. So these are the things that, you know, normally we use on the different type of modified electrodes. Okay, how are the electrodes being modified? Okay, so first we are looking into the fabrication. So one of the area that we're going to look into is on the fabrication. In this fabrication method or technique is to deposit or to coat the conducting material on top of the substrate. If you look at this diagram, this is one of the example where we have zinc peroxide nanoparticles, okay, and we coated with the polypyrrole. Okay, this one is we can do it via chemical reactions, and we coat the zinc peroxide on top of the polypyrrole. Okay, and then what we can do after that, we coated the glassy carbon electrode. So when we coat the glassy carbon electrode, we call it glassy carbon modified electrode, because the glassy carbon, on top of the glassy carbon, we have all these zinc ferric and also polypyrrole core shells. So this is where we do a modification. This modification also we call it fabrication. Okay, so we want to make sure that the unmodified electrode in the beginning, and we coat with something materials, conducting materials on top of that, and then we call it a modified electrode. So there are a few types to prepare modified electrodes. The common one is what we call it drop casting. So we just drop solutions of the electroactive materials on top of the substrate, and we leave it for evaporation for a certain time. It depends on the thickness of the coating materials and the amount of drop material that been casted on top of the electrode. The other method that can be used, or the other technique that can be used to put material on top of the substrate, is called a spin coating. So basically the electrode being spinning, okay, to get a homogeneous material coating on top of the electrode. So this is basically normally being used, very much being used in industry, especially in industry, which referring to like chips, chips, electronic devices, so that they want a homogeneous surface of an electrode so that it can behave homogeneously. So these are called spin coating. The other techniques that can also be used is called electrodeposition. This one is we have to either reduce or oxidize the coating materials on top of the electrode. So we're going to push or to look into potential boundaries between the possibilities of the coated material coat on top of the electrode. So these are called electrodeposition. Basically, you use electrochemical method to deposit the electroactive species on top of the substrate. The other one, we call it polymer coating. Polymer coating also can be used, to deposit polymers on top of the substrate. And we can also do like technique called functionalize. Okay, functionalize means after coating material on top of the modified electrode, they can also be functionalized. Again, you can do a two-step synthesis, or maybe one step is electrodeposition, another step is actually chemical reactions to functionalize the material coat on the surface of the substrate. And then we can also look into the technique called electrostatically bounding. So this one will give you some example later part of the lectures. So you can see how this material be electrostatically bounding with the substrate. Okay. So what important here is, in most cases, okay, the layer or the coating on the electrode surface is electroactive. Definitely, because that's where the electron transfer reaction can happen, because our intention is to make an electroactive layer and a modified electrode. Okay, so where in cases of this, we must make sure that it can exchange electrons with the underlying substrate material and be oxidized or reduced, because we know that we use a substrate. So in this case, when I mention substrate, is actually an electrode. Okay, like we have carbon, we have platinum, we have silver, and so on. So modified electrode is we modified the electrode and coat or put a layer of electroactive species. So in this particular case, we must make sure that both are actually conducting, so that when you set up an electrochemical cell to do any reactions, it can conduct electric. Okay, where the most important is can have ion or electron exchange on the surface of the electrode. So these are several techniques. So we go and more examples later. So when you look into this, these are the some of the examples that have been mentioned much earlier. All right. So drop casting, okay, whereby we have when we drop cast on top of the substrate, okay, so that it lets evaporation and the substrate will stabilize and form a layer on top of the substrate. Okay, then on the bottom part is actually the spin coating, okay, where the substrate, okay, being attached with a spinner. All right, so it's spin coat, and when you drop cast, you got another thin film and let it evaporate. This to make sure that you can actually on this spinning method is a lot of advantage. One, as I mentioned much earlier, it gives you a homogeneous surface area, and also you can control the size of the thin film, okay, depending on how much you coat the material on top of the substrate. Okay, so when you talk about layers, the conducting layers or electroactive layers on top of the modified electrode, okay, we are talking about, we want to form a mono layer or a multi-layers, okay. The most challenging skills needed, when you want to do a mono layer electroactive, okay, because mono layer is just a one layer. of electroactive materials. But this one is very, very challenging because you need to control the amount of materials, that can form on top of the substrate. So this can be formed on electrode by several reactions. For example, we call it irreversible absorption. Means one, the chemical being absorbed on the surface of the substrate or electrode is actually non-reversible. Okay, it stays as it is. Or you can also form a monolayer by having a covalent attachment. Okay, so one bonding, one bond between the substrate and also the material of your interest, basically your electroactive layer. Or you can also do monolayer electroactive layer is by organized assembly. We'll see later the example, but this one is the monolayer electroactive layer is the most challenging that we want to form on top of the substrate. For multi-layer, there are different techniques also can be done. And for multi-layers, presumably is very much used because the most important that you can control the thickness of your layers. So it depends, you can have multi-layers of electroactive layers, but again, you can also measure the thickness of your material deposited on top of the surface. So you can do a common one that I mentioned much earlier. Just do drop casting, spin coating, electrodeposition for polymer layer. So these are the techniques that can be used, okay, to deposit or to stabilize multi-layers or looking at electroactive layers on top of the substrate. So let's go one by one, looking into the example, okay, because we know that when we talk about monolayer, this is the most challenging, all right? So you want to make sure that the monolayer is just one layer of electroactive materials being deposited on top of the substrate. So one of it, as I mentioned, how to form it is using irreversible absorption. Okay, it's actually a non-reversible process. Okay, so you can look at once the particle or the material be absorbed, can neither diffuse along or nor dissolve from the surface. Okay, so basically in this particular case, we want to make sure that it just that material being deposit or being absorbed on top of the substrate. So in this case, many substances spontaneously absorb a substrate surface from the solution, generally because the substrate environment is energetically more favorable than that in the solution. So this is the challenge part where you might also have other substrate, but have to control the conditions so that you can only absorb the one that of your interest. So if you look at this example, we have three types of substrate or three types of electrode. One is called a mercury, okay, and the second one is platinum, and the third one is a gold, okay. So whereby in this particular case, we know that silver have a strong bonding between the sulfur, so you can have sulfur bonding on top of the mercury, okay. And we can also see other characters. So in this particular case, we must make sure that we know and understand what type of reaction can happen between the substrate and the target electroactive layers, okay. And you can see that how this can be formed on top of the substrate. So this is also one of the areas that also a lot been studied, especially looking into a monolayer of electroactive materials on top of the substrate. So you can have different substrate like what example we given here, either mercury or other type of electrode. Okay, so this is where you can actually see how the metal or the substrate or the electrode can actually have a strong interaction between the electroactive layers. Okay, on the other hand, we are looking into other examples, okay, like, some species find the surface of the electrode much more hospitable than the bulk solution, and so they will attach spontaneously to the surface. For example, we have some organic species, okay, such as those containing double bonds are often hydrophobic and strongly absorb from aqueous solution on carbon or platinum surface. So we have to understand the behavior of the species or the electroactive materials and also the substrate, where in this particular case, when you want to have a monolayer deposited on top of the substrate, they must have a interaction can be done, either looking at more electronegative species or looking at the double bond like what in conjugated system, that can have an electron that can strongly bind or bonding or interact with your substrate. So these are some of the examples, like when you have metal ions, okay, so that normally would not absorb can take place by anion induced absorption. In this case, you can see the strong absorption of an anion in the case of cyanide on mercury that can act as a ligand for a particular metal will induce its absorptions on the substrate. So for example, in this particular case, you know that you have a mercury as your electrode, okay, electrode system, and you choose the metal organic substance who actually electroactive species who can actually bind or have a strong correlation between the substrate and also the layer, the monolayer of the electroactive layers or electroactive materials. So in this case, we can see that the mercury have a very strong bonding with halides, okay, the negatively charged species, okay, that bind one layer of electroactive materials on top of the mercury. So this is where some understanding be needed for us to understand how this can be done, okay, using absorptions method. And we call it irreversible absorptions because only a layer or monolayer can actually absorb and take place by these electroactive materials. Okay. So the other one is, we call it covalent attachment. This is also another example of monolayer, because a monolayer is where we want to have a very thin layers of materials. So for monolayer, there is also another technique called covalent attachment. So talking about covalent itself is very strong reaction of bonding between the surface and also the electroactive layers. So this where we can see a strong attachment to the substrate will take place by covalent linking of the desired component to surface group. So in this case, we are looking into chemical reactions that can be carried out to form bonds between the substrate and the molecule of interest. For example, we can see, for example, down here, a metal or carbon can be oxidized so that the surface can be considered as consisting of hydroxyl groups. Such a surface can be selenized by reaction with an organosilane and then reacted with another molecule of interest. So in this case, the silane is a kind of glue for fixing the molecule to the surface. One would expect that this technique would also only form a monolayer on the electrode. So the salinization reaction causes polymerization to take place and thicker layers equivalent to several monolayers form. Okay, this is also one of the interesting topic that depends on the type of the organic, electroactive organic molecules, whereby they have the metal attaching to organic, but in this case, we know that we have a nitrogen base, amine base, also a reactive materials to be deposited on top of the substrate. So in this case, like you look at the diagram A, where you have a substrate carbon or other metal, okay, that have a hydroxide group, and this can be react with any materials, okay, and form a covalent bond. And in this particular case, when we form a silane group on top of the surface of electrode, we can also do functionalization. At first, we have only amine, but we can do another functionalization to form carbonyl group with alkyl group on top of that. So these are a few steps, that can be done to look into a different, a strong covalent bond with only a monolayer of electroactive species. And then we can do a chemical reaction to change the functionalization group over here and make it expose more functionalization, or looking into a longer chain of material on top of the substrate. So this again is actually a monolayer monolayer electroactive material on top of the substrate. So this is very interesting study, okay, whereby some organic synthesis knowledge needed as well, besides looking at how we can do a modification on top of the substrate or the electrode. Another example for covalent attachment is looking at how we can do electrochemically. Okay, this is also a very interesting studies made. Okay, if you look at the example given below, okay, we can employ the organosilane, okay, that is attached on the covalent bonding between the substrate and also the organosilane electroactive species. Okay. And then they can do other linking agents, okay, to make it more electroactive. So you can actually expand the organic or the species, okay, the monolayer, to a more functionalized material. And this one actually can be done either chemically or electrochemically. So we can actually look into how we can do it using cyclic voltammetry to look at the functionality and expanding, okay, the functionalizations of the organosilane group. And the second example is where you can have a graphite, which is actually a carbon-based substrate, and then you can have a covalent bonding between them to the carbonate group, and then you can also extend it to another metal organic compound. Same goes to the other example, glassy carbon, where you have a covalent bonding between a glassy carbon and oxygen here, and then you can actually expand it to more electroactive layers on top of the substrate. So, but in this particular example, we are looking into covalent bonding between one layer of electroactive species. But on the other hand, you can also expand it to more functionalization of that. So these are examples that very much used if you want to study more on the electrosynthesis. Okay, one of the applications that you can use modified electrode is looking at electrosynthesis studies. Electrosynthesis, including the mechanistic studies on the molecule of your interest, and then also looking into how you can actually do a lot of simulation, okay, using cyclophotometry as your electrochemical method. Okay, the other last one for monolayers is organized assemblies. Okay, we are still talking about monolayers. Okay, in this particular case is organized assembly. If you look at the diagram here, it looks like very organized. Okay, whereby you have a layer of materials, okay, on top of the gold electrode. So in this organized assembly is a spontaneous process leading to a structure with some degree of order imposed by lateral interactions among the component molecules. So monolayers of surface active compounds can be transferred from the liquid or air interface to the substrate surface. For example, you can see an organized monolayer can be formed on stannum oxide surface by using a firm balance to transfer molecules consisting of a biologen head group with a long chain hydrocarbon tail. Okay, so these are examples. For example, in the particular diagram shows layers of organosulfur, okay, which is have a thiol group, SO group, compounds with long chain alkyl groups of gold. Okay, so the thiol head groups will bind tightly to the gold. So the circle here is actually referring to the thiol groups, and the lateral interactions between neighboring alkyl chains create a regular structure in which the chains are extended in parallel at an angle from the normal. So this shows organized assemblies, where you have a very the functionality of the tiols, okay, will actually have interaction with the gold electrode. So the gold electrode is a substrate. So we are looking into electroactive layers. In the case of this, it's actually organosulfur group, okay, with a long alkyl chain. And you can see the interaction between the gold electrode with the thiol group, the SO group, okay, that hold them together with the long alkyl chains, okay. And you can see that, you know, it actually gives you a very the same, you know, how it binds, you know, the assemblies of the material binds in a very coordination way. So you can see that this is actually a monolayer of that. Okay. So then we move to a multi-layer. Okay, we have actually gone through monolayers. Now we are looking into multi-layer conducting material, which is more on electroactive layers on top of the electrodes. So then we can do a modified electrodes. So the common one, we call it, you know, the drop casting. The drop casting, as I mentioned much earlier, is quite straightforward. You drop cast on top of the substrate and you let the material evaporate, and you can actually get something putting on the surface or deposit on the surface of substrate. But on the other hand, we also have spin coating. Spin coating, basically, we want to have more uniform, okay? And as I mentioned earlier, in industries like, you know, productions of chips, they're very much using the spin coating techniques, you know, to form more uniform films. The other techniques used for multi-layer deposition on top of the substrate, it calls electrodepositions. So this one is using electric current. We control the potential, okay, on the conducting material, and then we can see how the electroconducting material being deposited on top of the conducting material, on top of the substrate, okay. And the other one is anodization. This is also electrochemical method, whereby in this particular case, we can use some metal, okay, that can be produced using anodizations or metal electrode, such as aluminum and so on. So this one also, we can actually measure the thickness of the film by looking at how much, what are the potential range that we apply, okay, for this ionization, and depending on the time as well. So these are some of the techniques that can form a multi-layer electroactive materials on top of the electrode. We go one by one, the examples, okay. These are, if you look at the same diagram that I'm showing you much earlier, the spin coating, so it's spinning. So this is mostly actually a customized machine that you can use. The most important that they can spin, okay, they have a plate who actually can spin the electrode, and then you drop cast your material on top of that, and then let it stable, okay, spinning to get a homogeneous thin film on top of the electrode, okay. And then it depends on the rate of spinning as well, because depends on how much material you drop cast on the surface of electrode, and also the spinning rate. So then you can look into the product that can form on top of the electrode. The other one is called electrodeposition, okay. So this one of the example that people usually understand is on electrolytic deposition, okay, where we can produce thin films of metallic coating using electric current, okay. And then you can see that how metal being deposited on top of the electrode, okay. Like for example, these are the examples, okay, where you have the working electrode, okay, directly under here, and you have like a carbon layer, which is actually a carbon conducting material, okay, and then you try and deposit platinum, okay, to form a platinum layer on top of the carbon layer, so that it will be more conducting. So this called electrodeposition method. We can control the structures, you can control the shapes and size of the electrocatalyst on the surface of electrode by altering the conditions of electrochemical depositions. because normally this method, this is quite a cheap method. You can use, for example, salt, the platinum salt, and then you can deposit platinum on top of the carbon layer. Okay, so in this method, electrodepositions, considering because salt is considered not very high cost of material, but using the salt, you can actually deposit platinum on top of the substrate. In this particular electrochemical deposition method, there is another good point that no capping reagent or surfactant or other dispersion agents is involved. Therefore, the synthesis produced can be greatly simplified because we know that electrodepositions at what potential that the platinum ion can be converting or reduced to a platinum. Okay, then we can control the potential at where we are targeting only the platinum can deposit on top of the carbon. That's why if you look at this method, is very much used, okay, for certain ion that can be deposited on top of the substrate. The other one, as mentioned, is an ionization. Okay, this one basically again another electrolytic procedures. Okay, whereby you electrolytic treatment of metals, during which stable forms or coatings are formed on the surface of the metal. Again, in this particular case is an anodization. Okay, so this one is basically you can look into how you can actually deposit. So in this case, some metal oxide can be produced using anodizations of metal electrode, such as aluminum oxide on aluminum anode in acid solution. So the thickness of film can be controlled by the applied potential and the anodization time. So you have here anode, okay, as aluminum anode, and you have a negative cathode, okay, whereby you can oxidize to form an aluminum oxide, okay, for this particular reaction. So this is called aluminum anodization, where you can actually apply the right potential for aluminum oxide to be deposited on top of the electrode. Okay, we have actually gone through the the monolayers and also multi-layers. So now we go for the examples of polymer layers. Remember that we have actually gone through different types of polymers on our first lecture. We are looking into like penny and so on. So they have a different material preparation. One of it is basically using a simple chemical reaction, and the other one is using electrochemical reaction. But how do we do polymer layers on top of the substrate? So one of the method used is by dipping the electrode into a solution containing a dissolved polymer such as polyvinyl ferrocene and allowing the solvent to evaporate. One forms a thin film on the surface. So this one is very like a straightforward, okay, that you can do polymer layers because this one is just using a solution that contain the polymer, and then you dip the substrate or the electrode, okay, and then let to evaporate, and you can form a film. But there are other other methods as well, okay, because the polymer it is very interesting electroactive layers that can be studied, especially looking at more stabilized coating material on top of the electrode. Okay, so the other method that can be used to form homogeneous polymer film are like deep coating, spin coating, electrodeposition, covalent attachment via functional groups, and so on. If you look at the methods, that can deposit the electroactive material on top of the substrate, I mean, the common being used is just what I said much earlier, is spin coating, or to get a more homogeneous, or you can do electrodeposition because you can control the thickness, you can control how much material should be deposited. You can also looking at more, functionalizations of that coating material. So let's look into a few types that have example here. Like you want to look into electroactive polymers, you can oxidize or reduce that groups covalently linked to the polymer backbone, such as polyvinyl chlorosin, or you can also do a coordinating ligand-bearing polymers that contain groups that can coordinate to species like metal ions, such as poly-4-vinyl pyridine. Or you can also do ion exchange polymers. So in this particular case, it contains charged sites that can bind ions from solution via an ion exchange process, such as Nafion and polystyrene sulfonate. Or you can also do electronically conductive polymers, such as polypyro and polyaniline, where you can use biological polymers, such as enzyme and other proteins, or you can also use blocking polymers. Okay, these are all the type of different polymer coating polymers on top of the substrate, because we know that polymer can form as a layer by layer, and it can be also being interconnected, between layers with a good functionalizations of the polymer. So these are actually a common, how you build up polymer on top of the substrate. So you can do like ion exchange, you can do like coordinating with other groups, you can also look into more conducting or other functionalizations, and covalent bond to the backbone, to the polymer backbone. So these are the stacks, of polymer layers that you can form using the modified electrode. So these are the things that a lot of studies being done as well, because the characteristic of the polymers that more stable and have a big group that can actually give a bigger surface area, because every monomers can have a different active positions that can actually give a surface for electron transfer. That's why polymers has been quite an extensive use in conducting material, because of the behavior of the polymer themselves, because they have a backbone, and also they can also have more functionalities on the surface of the backbone. So this is why polymer is very much used in the study of conducting materials. Okay, let's look into the next part. Okay, we have done on the fabrication. The first fabrication part of techniques is actually to give you the understanding how these electroactive materials can bind or can stay on the surface of the substrate. So we are looking into several examples. Okay, now we look at what are the process that happen on the surface of electrode. Okay, so we know that on the surface of electrode or on the surface of the substrate, we want the surface of the electrode to be conducting, because it can actually allow the transfer of electron. Okay, so what happened here when we study the process? Okay, we want to make sure that the modified electrode remains a field of high activity. Okay, whatever, because you have started with a conductor, which is actually the electrode themselves, and then again you coat with another electroactive layers. So we want to maintain they have a very high activity. Okay, we want to allow more electron transfer happen, on top of the electrode. That's why we need to do modified electrode. Okay, at least they can form maybe double or triple than the actual substrate performance. So many new types of surface structures are being prepared, and electrochemical studies are leading to better insights into the way charge is transported through surface layers and how charge is exchanged between surface species and molecules in solution. Okay, let's look into the diagram. Okay, the first layer on the left-hand side is your substrate. Your substrate can be carbon, can be silver, can be gold, can be platinum. So these are the first substrate. The second layer is your thin film, is your electroactive layers or conducting material that you deposited or you coated on top of your substrate. Okay. And then on the right-hand side is a solution of interest, because when you do electrochemical studies, it's always a heterogeneous reaction. Okay, it's solutions and also your electrode. So mostly your electrode is actually solid. So what happened in here? So you look into the process. The first one is, if you look at the first one, is heterogeneous electron transfer to reducible substrate in a form P to produce the reduced form Q. Okay, so this is where it happens. All right, so we reduce, okay, and form a Q. All right, so we have your first materials of P, okay, and then to produce Q. Then electron transfer from Q to another P in film, which is actually, this is what happened in your film. Okay, and then you can see that you can form continuous forming, okay, P to Q, Q to P. So more in equilibrium state. And then the third one is, what happened is that the electrons transfer from Q to a solution, in a solution at your solution interface. So this one is on the electrode, the first electron transfer happened, okay, between a substrate and also your thin film. Second is actually happening in the thin film itself, okay. And the third one, the P will convert to Q and the Q will react on the solution with A. So this is where another electron transfer happened, okay, on the surface of the thin film with the solution. So then you can see penetration of A into the film, okay, and then you can see on the 5 where a mass transfer of Q within the film, and then you can see a movement of A to a pinhole or a channel. So this where you can see that, you know, these are the things can be done, the process that can happen on the surface of electrode, where you have thin films of conducting materials on the modified electrode. So this all process can be studied, you know, with different techniques. Okay, if you look at the first example, you want to see how the thin film is actually coordinating themselves in terms of producing more electrical charge, okay, whereby you can see that, you know, transfer from the first substrate to the layer and then from the layer to the solutions, okay, and then you can understand what happened, the whole mechanism of reaction with different applications of that modified electrode. Okay, so then you can understand how you can convert A in a solution to another species, or coating another A to another material, or they can form another layers of here. So these are the process that can happen on the surface of the electroactive layers on top of the modified electrode. So it depends on what type of application that you are studying. You can actually relate that, okay, what actually happened on the surface of electrode when they can give changes in terms of chemical reactions of the target solution. So these are about the process. So you can understand the whole process of behavior, so that, you know, from there you can actually do a lot of characterization method. So we move to another part. We call it characterization. We need to have this characterization to understand the type of the electroactive layers being deposited. We want to know the size. We want to know the thickness. We want to know what can be done, or again, the next level of understanding of how these electroactive layers can form, you know, in certain reaction. So a few examples I'm sharing with you, because these are the things that, you know, need to understand and characterize. So once you do a modified electrode, we call it modified electrode because you have actually modified the substrate, which is actually the first electrode, and then you form another material on top of the electrode. So you have actually done your modified electrode. Okay. So after the surface of an electrode has been subjected to treatments, treatments is where you fabricate, okay, your electroactive layers. It is possible to determine the amount of material on the surface, its compositions and structure, and how easy it is to oxidize or reduce. I mean, the next level of it, okay? So means whatever you have actually deposit or coating, okay, with a substrate, you need to understand the type, the compositions, you know, to confirm that this is what you've been coated or deposit on top of the substrate. So one of the method that I'm going to share with you, what we call it electrochemical method. And the second one is spectroscopy method, and other methods also can be done. But these are the two common things that we need to identify, okay, the type of thin layer or monolayer or multi-layer that you have actually coat on the surface of substrate. So for example, electrochemical method, even a monolayer amounts of material can be analyzed electrochemically, since small currents can be measured quite readily. So a detailed inspection of the nature of the response and the shape of the curves can provide information about amounts of materials, chemical interactions in the films, and the rate and mechanism of charge transport through the films. So it is very important to understand electrochemical method. I do understand that most of you students have actually learned a few electrochemical method much earlier. So you can actually have some knowledge in that and how this will relate on providing information about the electroactive materials that being coated on the surface of substrate to form the modified electrodes. The other common technique used to characterize is spectroscopic techniques. I think the best is actually looking into, for example, we have electron spectroscopy. Okay, these can be used for analysis of the elements, presence in the surface of layers. Okay, you can also use direct optical spectroscopy measurements using visible IR and UV regions, either looking at absorptions or reflectance, depends on your materials. I'll give you some examples later, okay, why we need to study both. At least both can give you as much information on the characterization materials that you have done. On other method, you can also doing like direct observation of the surface. The optical or scanning electron microscopy is also often used to provide information about the texture and porosity of the layers. There are quite a number of techniques, that can be used when you're talking about material, because this one is material that you coat on the surface of substrate to form a modified electrode. So it's not easy for you to see from your bare eyes, it's not easy. But I give you an example. I had an experience when I do electrode deposition, electropolymerization, means you do polymerization on top on top of the substrate, which in my case, I'm using platinum electrode. And then I'm doing electropolymerization to coat polypyrrole on top of the on top of the platinum. So platinum, if you use your bare eyes, you can see it's just a silver color. But once you coat polymer materials on top of the platinum, you can see the color change to it's a beige, it's a black color, like purplish color. So from the purplish color, you can see that, oh, your polymer has been coated on top of platinum. But to measure the thickness is different. So you have to have different technique to measure the thickness of the coating material. We move on to examples, okay? I hope that you have understand about cyclic voltammetry. We have linear sweep voltammetry, we have cyclic voltammetry. So we just move to first one. We go it very fast, but I hope that you understand about cyclic voltammetry, okay? Where you have this potential range between one point to the other. You have initial and you have where the sweep potential will be, and then you're going back to the inner potential. That's why it's called cycle. It's a cycle between initial going to the sweep potential and then going to the initial potential back. So it's actually a cycle. So that's why it's called cyclic voltammetry. And then you can see the behavior as you increase the potential, the current also increase, and it has a peak on the forward scan and second inverted peak on the reverse scan. So in this particular case, you can see oxidation induction observed in the forward. So means you can have, let's say the potential is here, you scan the potential from this point to the other point. Okay, the first forward scan, you can see a peak A, B, C, and then you have a reverse potential scanning back, and then you can see a reverse span. You can have it, when it go to more negative potential, is reduction. So you can see another peak reduction occurs. So this cyclic voltammetry is generally used to study the electrochemical properties of the electroactive layer in solution or of a molecule that is absorbed on top of the electrode. So they can use both. Okay, once in solution or the modified electrode. You can study the modified electrode using cyclic voltammetry. That's why a lot of studies, for example, in my case, in my work, in a student's work, normally they use the first electrochemical method to look into the first understanding, the first scanning of the materials they're using cyclophotometry. From there, they try to understand what happened, and we relate to other techniques as well. So this cyclophotometry basically is a basic electrochemical method that used to identify the type of material coated on the surface of electrode. Sorry for that. Okay, let's look into more example of cyclic photometry. Okay, so again, when you talk about cyclic photometry, we are looking into the electrochemical response for the electrode reaction. For example, you're looking into reduction, and then it can be affected quite significantly by absorption of oxidized or reduced species. It depends. Sometimes, you know, the cyclic photometry shows this one is a very nice reversible reaction, where you can see the forward scan, you can actually have oxidized species, and then when you reverse back, you can go back to your reduced species, and then the reduced species being oxidized back and do reduce and reduction. So oxidation reaction occurs. Okay, this is a reversible reaction. So to understand more, you can see that if oxidized species, O is oxidized species, is absorbed more strongly, the peak displays toward negative potential. If R is absorbed more strongly, so the peak displays toward positive potential. Okay, you can actually look into this. Either you can start with positive potential towards negative potential, or you can start positive potential towards negative potential, or you can start from negative to positive, positive to negative. Either way, actually, you can do that. Because when you do a first scanning to look into the type of material, you have to have this bigger picture, okay, where you can see the peak to understand more. When lateral interactions exist between O and R in the film, okay, the cyclic mathematical shape is governed by the interaction parameters, okay. So CV, cyclic mathematics, is often used to study a variety of redox processes to determine the stability of reaction products and the reversibility of the reaction. CV can also be used to determine the electron stoichiometry of a system, the diffusion coefficient of an analyte, and the formal reduction potential of an analyte, which can be used as an identification tool. That's why I said this is basically a very basic electrochemical method that can be used to identify the behavior of species on the surface, on the modified electrode. Okay, because if you know what are the substrate being deposited, you can understand more. For example, you expect the hydroxide group being oxidized to carbonate group, for example. Okay, after you know leaving electrons behind, and then you can see that it's oxidized, and then you can see peak. You know, the first peak actually occurs on the cyclic photometry. So these are the basic characteristic of identification, okay, of the material that been deposited on top of the substrate. The other electrochemical method that can be used is electrochemical impedance spectroscopy. This is very challenging. Okay, this needs a lot of understanding, but it is a powerful technique. Okay, because a lot of advanced studies on materials, they are using EIS. We call it in short EIS. We are looking into the charge transport across the electroactive layers and its interface. We also can understand the electrode kinetics, and we can also understand the double layer studies. So these have a wide range of frequency. They measure the response, compute the impedance at each frequency, and finally plot two different graphs. So we need to plot Nyquist plot, we call it, where you can see the resistance, okay, of the two plot. And then you can also do a dot plot. So this one has to go very deep into the study so that you can understand more. It's quite complicated. You need to set up the cell so that you understand how this charge transport being characterized using both. You must have Nyquist plot, and you must have dot plots to understand more. So then you can measure, you know, the conductivity of the material, or the thickness of the layers, and so on. Just a lot of studies can be done on this EIS. Okay, if you look at this example, okay, so EIS is basically the treatment of electroactive layer that can be modeled as a network of passive electrical circuit elements. So this is actually the model study has to be understand first, okay? Then you can actually form a simplified version of your network into a circuit element so that you can understand the behavior of each of the circuit elements that being positioned, okay, and form a cell so that you can understand in bigger picture. So a network is called an equivalent electrical circuit. Okay, so this equivalent electrical circuit is you have to try and error to look into the best cell that can perform to understand the whole behavior of your electroactivity on top of the substrate. It can be done using serial and parallel combination of circuit elements. Okay, so these are some of the examples that can be understand if you have resistor, capacitor, inductor, and so on. Okay, you can it helps you to actually model the circuits, okay, so that you can have a common understanding. For example, if you look at the right hand side, okay, definitely you have electrolyte resistance, which is actually the RS, okay, and also here on top of the electrode, you can also have double layer capacitance, which is actually between the electrode as well as between the target species. And then you can have electron transfer resistance. Again, the electron transfer resistance happen on the surface of electrode. And you have Warburg impedance, ZW. So this one is also being calculated, okay, looking at impedance that can happen in between that, okay, and also constant phase element, which is actually the key. So in this particular case, if you look at the circuit, the simple circuit that we made, because it involves only double layer capacitance, involve resistance between the layer of the materials and the surface of the electrode, and also the resistance from the solution. So these are the simplified versions of cell that can understand on the EIS. EIS, we need to have a long, discussion on this to understand. It cannot be done within this short period of time. There's a lot to understand more, but this is the simplified version of how we can understand to make sure that you understand the whole system of these electroactive layers. So the one that I've mentioned to you, the second technique is actually spectroscopy technique. This is very straightforward that you have actually understand. I hope that you have heard about XRD, X-ray diffraction, and now we are looking into electron X-ray photoelectron spectroscopy. Is XPS. XPS is very expensive equipment. In Malaysia itself, we only have two XPS in the country, which is very expensive. And you can see from the view photograph here is a very dedicated and sophisticated equipment, okay, whereby you can study surface analysis, okay, to determine the elemental composition and oxidation states of elements at the surface of electroactive layer by excitation of inner orbital and bonding electrons by a focused X-ray beam. So means you can study the elemental composition, you mean the total amount of certain elements. For example, you're talking about silver total, and you can also look into if there is any oxidation states of that element, okay, on the surface of electroactive layer. This is a very powerful technique that can be used to characterize. So XPS is extremely good for surface analysis of electroactive materials after treatment. This is because the kinetic, the energy of the escaping photoelectrons limits the depth able to be probed. When a sample is irradiated, the electrons ejected are from the inner shells of the atoms. So using XPS can be determined different changes in electroactive layer after treating, such as elemental composition, empirical formula determination, chemical state, electronic state, binding energy, and also layer of thickness in the upper portion of the surface. So you look at the diagram here, because when you talk about XPS, this is again X-ray photoelectron. X-ray photoelectron is very expensive, but they have a target optical way of how they can actually target the right elemental compositions on what we are targeting. So it gives you a total element composition, or maybe looking into a different chemical state of your element, so that you can understand how much, you can have look into that. There are more characterization method, okay, like what we mentioned much earlier. We can have even, we're looking into, but we are talking about more on solid state material. Okay, you have to look into solid state material. For example, you can also tunneling electron microscopy also can be used, TEM. Okay, especially when you want to look into the size, the layer, okay, of the material, so you can actually use that as one of the spectroscopy method. The common one that you can use is actually UVVs or IR. Okay, so that's very common one. I think most of the laboratory have this. Okay, they use the UV spectroscopy. So UV spectroscopy basically is a quantitative technique. You can quantify, okay, used to measure how much electroactive layer absorbs light. Okay, this is done by measuring the intensity of light that passes through a sample with respect to the intensity of light through a reference sample or blank. Okay, so you can actually quantify, okay, the how much electroactive layers absorbs, okay, using this UV light. So application of electroactive layer in thin films have been widely used in solar cells, light emitting diode, as metal contact and semiconductors. These devices consist of films with thicknesses of about 1 micrometer, and it is important to know the refractive index, the thickness, and the absorption coefficient as a function of wavelength to predict the photoelectric behavior of a device. So knowledge of these optical constants is also necessary to determine the optical band gap. So this is one of the examples. Okay, I think this is quite common. I hope that most of the students know how to run the experiments using the UV spectroscopy method. But what important here is that it is possible to characterize electroactive layer using this method, because the electroactive layers have optical properties that are very sensitive to their size, shape, agglomeration, concentration changes. Hence, a method that is versatile, reliable, and economical like UVVs can be used for the in situ characterizations of electroactive layer, even at very low thickness. So this is the very simple method that you can study, okay? Because we don't know what are the, for example, you want to characterize, you have a carbonyl group in your materials, like in this example, you have silver and also PAH, okay? So you can actually study the PAH using this method to look into different concentration, and you can understand the behavior of your material using UVV spectroscopy. So these are the things that, one of the things that under study of this, so that you can understand what type of material that you coat on the surface of your substrate. Other method, as I mentioned earlier, is about TEM. This is transmission electron microscopy. Again, this also is quite an expensive equipment, but it can go up to the atomic, looking into the internal structure, okay, of the material using a beam of high energy electron transmitted through the materials. So is valuable technique for characterizations of microstructures. So when you use TEM image, we can cross-sectional images can be obtained, thus showing the pores through the thickness of the film. Look into this diagram here. Okay, you can have a cross-sectional images. Okay, it depends. You can also look into the thickness, and also you can look into this micrograph of the film. If there is any changes in terms of morphology, or in terms of geometry, in terms of space and spore, you can actually look into this micrograph. So the high resolution of TEM can be characterized crystals to very small dimension through both imaging and diffraction. For example, the layers of indium pergalinium as can be distinguished by the difference in image contrast that they display despite having the same crystal structure. You can see here they are, you can see like a layer over here that give you the differences between layers of materials that been deposited on top of the substrate. Okay, you can see this by looking into the TM micrograph. Okay, then you can actually identify which one is the one that you targeted for. So the texture of the electroactive layers after deposition on substrate depends on combination of the following parameters. One is looking at the layer thickness. You can measure the layer thickness because it's cross-sectional. So cross-sectional, you can actually look into the thickness. And then you can also look into crystallographic orientation in and out of the plane of the films, because you can rotate, you can rotate and see different direction and orientation. And then you can also see epitaxy with the substrate and other layers. Okay, you can see epitaxy, you can see the differences between the layers. And you can also look into grain size and orientation. And then you can also roughly see the physical roughness. If there is pores, if the agglomeration occurs on top of the surface, or you can see roughness of the surface, or you can see some pores occurring on the surface. And you can also look into atomic scale structure and effects. So TM is one of the powerful methods that used in electroactive layer, modified electrode studies. Not only that, this TM also can be used in most of the advanced material studies, like what we have actually looked into, like SRD, we use TM and other methods as well. So these are the things that, have to look into that, so that we can understand the behavior of the materials that being coated or deposited on top of your substrate. Okay, I just want to give you, before I end my lecture, because it is quite a very long lecture today, to look into the fabrication and to look into the characterization. So I just give you one example that being studied, okay, whereby if you look at here, we have substrate called GCE, which is actually glassy carbon electrode. And then we deposited using PANI, okay, PANI is polyaniline. Okay, using electrodeposition method. And after deposited of this PANI, we also do some application where we reduce hydroperoxide to water. Okay, what we study when we do the characterization of this PANI, we use XRD. Okay, in this particular case, we actually synthesize silver nanoparticles with PANI nanotubes. Okay, composites. So when we have the PANI, silver nanoparticles and PANI, we use XRD. So XRD, this is a typical peak for silver nanoparticles. So from the XRD, we can see that, okay, on the surface of substrate, we actually form silver nanoparticles. And then on the other hand, we also study FTIR. So from the FTIR of this substrate, okay, of this electroactive material, we can see peak. Okay, for example, we can see peak for NH. The NH peak is around here, so we can see NH in here. Oh, sorry. And then we can also see C double bond N peak somewhere here in FTIR. So we have PANI in there. So we have PANI, we have polyaniline, and we also have silver nanoparticles. So both being formed on top of GCE. So this one being studied. So these are some of the characteristics that are being used. And then we also look into the cyclic watermetry. So the cyclic watermetry being studied, looking into the bare GCE, which is nothing on the glassy carbon. And then once we coated with PANI, okay, we can see some changes in cyclic watermetry. And then we start coating silver nanoparticle, we can see some changes in the cyclic watermetry. So basically, we have done the coating material of electroactive material on top of the glassy carbon, and then only we try to reduce this, looking into the behavior of these silver nanoparticles with PANI. So you can see a big jump in here, and this shows, that we can do some reduction looking into how we can actually reduce oxidized pani at the more negative potential. So in this particular case, it was found that the response for that, we can see a reduction peak at about negative 0.6 volt. Okay, where we can actually, this is actually where we form silver nanoparticles pani. And then on the other hand, we can also study using amperometry. Amperometry is basically looking at how this electroactive material can reduce hydrogen peroxide to water. Okay, so this one being studied using amperometry, looking at different concentrations, injections of hydrogen peroxide, and you can see which area that we can actually detect hydrogen peroxide depending on the time and the current that produced using amperometry method. So these are all studies when you do silver nanoparticles, pani nanotubes composites. Okay, so that's where we understand how we can actually reduce hydrogen peroxide using the electroactive materials that been produced and being deposited on top of the GCE. This one example. The other example also, we are looking into silver nanoparticles, multi-wall carbon nanotube, and also reduced graphene oxide. We are to produce, the electrodeposition method. We try to reduce using this potential window between 0 to negative 1.5 volt, okay, to do electrodeposition so that you can deposit the silver nanoparticles and also the multi-wall carbon nanotubes together on top of the GCE. So we are studying using the cyclophotometry. So we can see the different reduction peak occurrence representing on the type of material, that can be deposited on the surface of substrate. So these are some examples that when we do characterizations, we want to understand at which peak, that's material being reduced or oxidized. So choosing the right potential window is important, all right? So we know what's happening actually in the solution, so that at the end, when you do electrodeposition, this is the one that you deposit on top of your electrode. Okay, so I think that's all for today. So hopefully the sharing information is benefit to all of you. Okay, if you have any questions, we can share together. Thank you.
Yes, thank you, Professor Yatima, for the nice lecture. I'm sorry, but Dr. Ahmad is having he's taking her son to the the hospital, so I'm replacing him now.
Okay.
Professor Yatima.
It's all
so
right.
For the student, is there any question?
I'm not sure whether it helps the students, but at least you have some ideas, for fabrication and characterization and understanding of it. I'm not sure how the students respond to this.
Yes. Okay. Do we have question for Professor Yatima? Maybe it's just like an opening question, Professor. So
Yeah,
I'm interested about the functionalization of the electrode. So what kind of how can I say, what kind of properties that we would like to seek to functionalize the electrode? For example, should we try to like kind of mix and match about the reactant itself? For example, if it's like what kind of reactant should be suitable for the amine functionalized group, something like that, or sulfonic functionalized group, something like that. Probably one for the opening question. Thank you, Professor.
Thank you very much, Prof. Okay, regarding the functionalization, these are actually the main topic is actually that we are looking at, because we want to make sure that when we form a functionalized material, it will give you more, sorry. When you do a, sorry, Okay, when you do functionalization, it's actually you're looking at more electroactive side. Okay, you have the backbone, for example, polymer. You have the polymer backbone. You know that polymer form a stable deposit or several coating material on top of the substrate. But on top of that, you want to be more active. The material can be more active in functionalizing it with other electroactive side. Okay, for example, hydroxide, for example, or amine side. So either you do it when you have coated the material, or you can also, like what I mentioned to you on monolayer, you can also add in more electroactive materials by having a chemical reaction. You can do everything in one pot synthesis, or everything is all together, okay, mixed up, because we know that we can have one pot synthesis or we can have different chemical reactions, okay. So you can actually plan for your reaction. If you want to do a one-pot synthesis, you want to make sure that if you're doing electro deposition method, is everything can be electro deposit on the target potential window that you are targeting. But if you want to do, for example, functionalization, is after the electro deposition, you want to make sure that there is possibilities of reaction between your reagent and also your material that can react, chemically, so that they can change the behavior to more functionalized active material. So the understanding of the organic synthesis part also has to be in our mind, so that we can plan for other functionality. For example, like what I've given to you, maybe you introduce aldehyde, okay, on the conjugated system, then you can have a carbonyl group, and then again you can oxidize it to do carboxylate, for example. So this understanding of organic has to be in mind, so that we can do the functionalization step by step, or you can do functionalization using chemical reaction, then do electrodepositions, or maybe continue it during chemical reactions, or you can do a one-pot synthesis. So that's very interesting studies actually. That's why we can do a lot of modification when we talk about functionalization.
Yes. So for the electronic active polymer, so maybe we have some research students doing their modification of electrode. Several are the students of Professor Rifandini doing also the modification of an electrode. So maybe you can give an insight. For example, if you wanted to have like electronic active polymer, which is suitable, for example, for the CO2 reduction to formic acid, do you have an insight what kind of electronic polymer that we can use for that one, Professor?
Okay, when you talk about carbon dioxide reduction, normally you're talking about amine base, okay, either amine base of in chemical reaction, normally we use that amine, DEA or some MEA, But when we talk about electro deposition method, for example, when we talk about electroactive layers or modified electrode to reduce carbon dioxide, you are looking at amine base. So you have to do some modification on the electroactive layers. Okay, at least it behave almost the same like what they behave in a solution.
Yeah.
So then you can try and do it. For example, polypyrrole as a backbone. All right. So then polypyrrole, yeah, you can do some modification on polypyrrole to get more diamine. All right. And then from there, you can actually have multiple reaction, can reduce carbon dioxide, for example. So the understanding of it has to be in mind, the targeted molecule, and then we do some modification on the type of polymer that used. I'm normally, when carbon dioxide, normally they use a polymer backbone as their base electroactive polymers or electroactive layers. And then after that, they do some modification so that they can attract more CO2 to be reduced on the surface of electrode. Then you can have a high potential of having conversion of this carbon dioxide.
Okay. Thank you very much, Professor Yatima, for the explanation. So again, is there any question? Okay, probably from the research group. I know that some of you under supervision of Professor Ivan. So probably you will, and also Dr. Rahmat Wibowo, probably you will need some kind of an insight from Professor Yatima to do for your research and also for other students. So go ahead, raise your hand. So yes, is there any question?
Are there any doctoral students here or master student?
Master students, I saw like one or two master student, Professor.
Okay.
So is there any question about this session about modification of the electrodes and how to characterize, because Professor Yatima mentioning about doing XPS, cyclic voltammetry, TEM. So
Maybe it's too heavy for the elective course. I'm not sure. Is it heavy for the elective course? But it's actually a good knowledge for them.
yes, because it's quite applicable, Professor. I mean, yeah, I mean, for the usually in the research student, maybe they should know about this one, especially what they're doing on the yeah, electrochemical method, something like that. So I don't know. So,
Yeah, I'm afraid as well for the third year student for the elective course.
yeah,
But I think it's good knowledge for them so that they can extend their knowledge later when they want to do for postgraduate. But
yes.
for postgraduate, I think they should also understand this, but maybe in a way that I'm not sure whether I try to be as as low as possible to make people understand.
So we have this in the chat box. So the students say, so far so good, Pak Ridwan. So
Okay.
maybe your explanation is it's easy for them to
Okay. Okay, that's very good.
understand. So that one.
Yeah.
Yes. So this is the last session, right, Professor Yatima? Is there any session in this for today?
For today, no. I've got another one lecture. Will be on the
Yep.
14th of April, but that
Yep.
one will be more on application. But at
Yep.
least some fundamentals on the electroactive layers and also modified electrodes being covered.
Yes.
So on the third lecture, I'll sharing more application and what my students are doing on this particular topic, so they can have more examples of research activities.
Okay. So so that case, I would like to thank you to Professor Yatima for giving this nice session about the application. I mean the modification of the electrode and then also the characterization. Probably for the next 2 weeks, you will go in very detail, probably Professor Yatima, right?
Yeah. Okay.
Yes. So maybe as usual, Professor Yatima, before we close this lecture, we will have kind of documentation. So I hope that you all of the students can open your video and we can take a picture for the documentation for this second lecture, second session of Professor Yatima lecture series. So Mbak Safira mungkin bisa dikoordinasi ya.
Baik, Pak. So please all of the students to open your camera. Okay. Okay, I will take the screenshot now. 1, 2, 3, smile. Okay, the second page. 1, 2, 3, smile. Third page. 1, 2, 3, smile. Fourth page. Okay. Thank you.
Oke, terima kasih Mbak Safira. Thank you very much, Professor Yatima, for the lecture. We will see you. We are looking forward for your next lecture on
Okay.
14th of April.
All right. Okay. So thank you very much semua. Terima kasih.
Thank you very much. Terima
Assalamualaikum
kasih.
warahmatullahi wabarakatuh.
Waalaikumsalam
Waalaikumsalam warahmatullahi wabarakatuh. Thank you so much, Professor.
Terima kasih semuanya.